Hello everybody, welcome back. Unit 1, Day 3, we'll call this, Day 2/3. Today we're going to talk about inverse functions and one-to-one. So what does it mean to be one-to-one, and how can we determine whether a function is one-to-one or not? Well, first of all, we're going to take a look at it numerically. The way you determine if a function is one-to-one numerically is you have to determine if each element of the domain has a unique element of the range. So what does that look like? Well, if our domain is the set 3, 4, and 3 gets mapped to 7 and 4 gets mapped to 8, we would say that that function is one-to-one because each element of the domain has a unique element of the range. 3 only gets mapped to 7. 7 only has 3 as a pre-image. Graphically, what does that mean? Graphically, that means that the function passes the vertical line test, which obviously it has to be a function, and the horizontal line test. That determines on whether it's one-to-one or not. So let's take a look at an example here where we have to determine whether the following are one-to-one functions. If not, we have to explain either from a graphing perspective or using specific values. So first, f of x equals 3x minus 1. That function is simple enough. You guys should all recognize this as a linear function. You could just do a quick sketch. Slope is 3. The y-intercept's -1, so it's going to kind of look like this. So a vertical line test, obviously it passes. How about a horizontal line test? Yeah, it also passes. So what we can say here is that this is one-to-one because it passes the horizontal line test. Okay, now you can't just say one-to-one because it passes the horizontal line test without providing a sketch. So if you want to use that test, that's fine. Just provide a sketch of what the function looks like. Okay, number 2. G of x equals x squared. Again, from those base graphs or parent functions that we talked about in the beginning of the unit, you should recognize this as a parabola. And right away, you probably recognize that this fails the horizontal line test. It passes the vertical line test, so it is a function, but it doesn't pass a horizontal line test. So I would say not one-to-one, because it fails the HLT, or does not pass the horizontal line test. Okay, let's talk about inverse functions. First of all, definition. F of x and g of x are inverses of each other if f of g of x equals g of f of x equals x. All right, the symbol for an inverse function is this notation right here, f of -1. It does not have the same property as your negative exponent, so don't think that. It's just a different notation that we use for functions. And you say the f inverse of x. And you notice here it does not equal 1 over f of x. So how do we find the inverse of a function? Let's take a look at this equation. C equals 5/9 f minus 32. This is the Fahrenheit versus Celsius temperature scale. So if I ask you for 95 degrees Fahrenheit equals what in Celsius, that's pretty straightforward given that formula, because I'm going to take 5/9 times 95 minus 32. So you take 95 minus 32, that's 63. You take 5/9 of that. The 9 goes into 63 7 times. 5 times 7 equals 35 degrees Celsius. So that's a pretty easy formula to work with. Now, question number 1 says, what is the formula for F? Well, what if I gave you the Celsius temperature and I wanted the Fahrenheit temperature? So what I want now is a formula that has F equals something in terms of C. So we're going to go through this kind of quickly. What we're going to do first is get rid of this 5/9. So I'm going to multiply both sides by 9/5, multiply by the reciprocal. So I'll have 9/5 C equals f minus 32. And then obviously I need to get this 32 over to the other side. So I end up with a formula that looks like this. F equals 9/5 C plus 32. So there's your formula for F. So now if I said, what is the Fahrenheit conversion of 25 degrees Celsius? Now I just put 25 in for the C. So F equals 9/5 times 25 plus 32. Okay, 5 goes into 25 5 times. 9 times 5 is 45. 45 plus 32, 77 degrees Fahrenheit. Let's move on to determining if two functions are inverses of each other. We set up above, if two functions are inverses of each other, then f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. So our first example here, determine if g of x and f of x are inverses. So what we need to do, and it doesn't really matter what order you do first, is I need to determine if f of g of x equals g of f of x equals x. All right, so let's do f of g of x first. So what we're going to do is take g of x and put it into f. G of x is the square root of x plus 5. Okay, so now what does the f function tell me to do? The f function tells me to take my input, square it, and then subtract 5. All right, so it's going to be input squared and subtract 5. Well, what's that input? It's the square root of x plus 5. Well, the square root of x plus 5 squared is simply x plus 5. Minus 5 is just x. Okay, so I have a pretty good indication here. Yeah, these are going to be inverses, but I want to show the other version as well. So g of f of x is going to be g of f of x, which is x squared minus 5. So now what I want to do is I want to take a look at my rule for g, which tells me to take the square root of my input and add 5. So square root of x squared minus 5 plus 5. Okay, so now notice all of this, I didn't draw that very well, but all of this is under the radical. So under the radical I have x squared minus 5 plus 5, which is just x squared. And then the square root of x squared is simply x. So now I can say inverses because g of f of x equals f of g of x equals x. Okay, let's take a look at example 2. So here I need to do, again, it doesn't really matter what order you do these. I usually go alphabetical order, so I do f of g of x first. So I'm going to take f of g of x. Okay, it looks a little bit more complicated here. Square root x minus 1 over 3. So now what you're doing is you're going to put that into your f function here, which says 3 times input squared plus 1. Okay, so let's see. 3 times input squared plus 1. And that input is this. Square root x minus 1 over 3. Okay, so now I've got the square root of x minus 1 over 3 squared, which is simply x minus 1 over 3. And then I take 3 times x minus 1 over 3, so those cancel. So here I get x minus 1 plus 1, and that equals x. I'm pretty confident that g of f of x is going to be the same, but again, we have to go through and prove that. So g of f of x is going to be g of f of x is 3x squared plus 1. And what does g tell you to do? G tells you to take the square root of your input minus 1 and divide that by 3. All right, so I've got the square root of my input minus 1 all divided by 3. And that input here is going to be 3x squared plus 1. Okay, so now, I know it's hard to read, I apologize for that, but in the numerator you have 3x squared plus 1 minus 1, which is just going to give you 3x squared over 3. Now those 3's cancel, so you have the square root of x squared, which obviously is just x. So once again, what we've shown here is that these are inverses because f of g of x equals g of f of x equals x. All right, last one. F of x is 3 over x minus 2. G of x is x minus 2 over 3. So let's see here. f of g of x is going to be f of x minus 2 over 3. So this is going to be fun. We're going to have a lot of fractions here. So what does the f function want me to do? The f function wants me to take 3 divided by my input minus 2. So 3 divided by input minus 2. Well, your input, remember, is going to be this. So now I'm going to have inside the parentheses there x minus 2 over 3. So I've got a complex fraction, and this is probably a good time to review some algebra that's going to be a huge time saver for you guys throughout this year. If you have a complex fraction, the quickest way to simplify that is to multiply each piece of this fraction by the lowest common denominator. So the denominator here is 1. The denominator there is 1. This denominator is 3. So I need to multiply all of these terms by 3. Okay, so in doing so, my numerator, 3 times 3, that's 9. Here, those cancel. So this is the beauty of this technique, is it gets rid of the complex fraction. So I just have an x minus 2 minus 2 times 3 there is 6. So this is 9 over x minus 8. Well, I'm done here because that does not equal x. So I'm going to say not inverses because f of g of x does not equal g of f of x does not equal x. So to disprove it, you only need to show that one case does not equal x. Okay, so now let's tackle how to find the inverse of a function. All right, we just determined whether two functions that were given to us are inverses of each other or not. How do you actually find the inverse of a function? Well, to find the inverse of a given function, first of all, you have to determine if the function is 1 to 1. If so, you're going to switch the x and the y, and then you're going to solve for the y. All right, so our next group of examples here, I want you to determine if f of x is a function. If it's a function, is it 1 to 1? If so, find the inverse. All right, so our first function, f of x equals x minus 3. Again, we should recognize that this is a linear function. This is the same as 1/5 x minus 3/5. So for part A, yes, it's a function. For part B, is it 1 to 1? Yes, because it passes a horizontal line test. So I want to find the inverse now. So this is given to us in function notation. Remember, this is kind of like our y. So to find the inverse, I'm going to switch the x and the y. That's going to become x equals y minus 3 over 5. So I'm going to go through the algebra quickly. We're going to multiply both sides by 5. 5x equals y minus 3. And I'm going to add 3 to both sides. So what that's going to give me is f of x plus 3. Now, since we're asked for the inverse and the original is in function notation, we have to use function notation to express that. So it's going to be f inverse of x equals 5x plus 3. There's our inverse function. All right, part 2, or number 2, g of x equals square root x plus 8. Again, from our base functions, square root graph looks like this. So for part A, obviously, yes, it's a function. Part B, is it 1 to 1? Yeah, that passes a horizontal line test. So now I need to actually find that. So let me shrink this up here a little bit real quick. Bear with me. All right, so again, what I'm going to do now is I'm going to switch my x and y. It's going to be x equals square root y plus 8. So the first thing I want to do here is I want to square both sides to get rid of that square root. So this is going to be x squared equals y plus 8, and then obviously I'm going to subtract 8 over there, so y equals x squared minus 8. So again, using function notation, what I'm going to have here is that g inverse of x equals x squared minus 8. Well, this isn't 100% correct, because if you notice, g inverse of x equals x squared minus 8 is a parabola. And clearly, if we take the square root graph and we reflect it in the line y equals x, it's not going to be a parabola. So we have to restrict the domain. And probably the easiest way to do that is to restrict the domain on the inverse by thinking what the original function's range is. So the range of the original function is y is greater than or equal to 0. So to restrict this domain, we're going to say x is greater than or equal to 0. Okay, question number 3, h of x equals 3x squared minus 1. Remember, is it a function? So that's a simple parabola shifted down 1 for the dilation of 3. So yes, it's a function, passes a vertical line test. B, is it 1 to 1? Does it pass a horizontal line test? No. So if it's not 1 to 1, there's no inverse. This next group, we're going to use the above functions to evaluate g inverse of 6. Well, what we're going to do to evaluate that is we're just going to take the g inverse function and plug in a 6. So we just found it. X squared minus 8, 6 squared minus 8, that's 36. 36 minus 8 is 28. F inverse of negative 2. Okay, so my f inverse function is 5x plus 3, so I'm just going to plug in a negative 2. 5 times negative 2 plus 3, that's negative 10 plus 3, that's going to be negative 7. Now this one here I need to change because we just established h does not have an inverse, so I'm just going to change this up. For your notes, just make this g of g inverse of 74. So you might think, well, if I have to do this without a calculator, I have to take 74 squared and subtract 8. I can't do that without a calculator, but one thing to note is this. You're evaluating a function at its inverse of that number. So all that happens there is you end up getting 74. Okay, and it didn't matter if I use g of g inverse or f of f inverse. If you use the function of the inverse function of a value, you just get that value. The domain of a function is the same. We did this last year in A2, is the range of the inverse. So don't forget that. We sort of talked about it up above. And inverse functions with graphs, please don't forget, given a function f of x, the inverse f of x, or f inverse of x, is the reflection of f of x about the line y equals x. And if you think way back to geometry, you remember your rules of transformations. When you're reflecting the line y equals x, you switch x and y. So if you know your coordinates, your ordered pairs, you just switch them and there's your inverse. Okay, last page, we're going to do this a little quick. Example 1, f of x equals the square root of x. That's one of our base functions. So square root of x, 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. So there's f of x. I want to find the graph of f inverse of x. So remember, we are going to reflect in the line y equals x. You can do this visually. Let me just sketch that in. You could do it algebraically by taking these ordered pairs and switching the x and y. So 0, 0, 1, 1, 2, 4, and 3, 9. All right, so you end up with this graph right here, and that's going to be f inverse of x. And if we want to know what that equation is, I know it didn't ask for it, but that looks like it's a parabola, right? So I'd say x squared. However, we talked about the restricted domain, comma, x is greater than or equal to 0. And the last one. F of x equals log base 2 of x. So here's what we want to remember with our log graphs. They have vertical asymptotes, and this one has not been shifted, so it's going to be the y-axis, or x equals 0. Goes through the coordinates 1, 0, and base 1. My base is 2. Okay, now I could go a little bit further if you wanted to also be 4, 2. So here's what this graph's going to look like. And so I want the inverse of that. We're going to reflect it over the line y equals x. So visually you can do this and then just flip those ordered pairs. So that's going to give me 0, 1, 1, 2, 2, 4. And now also, I should point this out, your asymptote is now going to be the x-axis. So what function is that? Well, that's our exponential function. So this is going to be the same thing as 2 to the x, because the base is 2. All right, so that concludes day 3 lesson. Please go ahead and do homework 3. You've got the answer key provided for you guys. And if you have any questions, as usual, please reach out and contact me. Thank you.